Today we will continue the discussion on surface integrals, but today we will do vector fields, not scalar integral. Now consider a surface S and there's a vector field F. So we can define something called a flux function, which is defined as the integration of this surface of F flux the field dot ds as a vector. So as a flux, it means we will pretend F is a flow, so we can see what is going through this surface. So if F and ds is parallel, so F is like normal, so we can say something is going through this surface. But if it's parallel to this it's parallel to the surface like that, then we'll say it's not going through. So F dot ds, this is the direction of n, which is ds. Okay, so if F is along n, then it's going through. If it's perpendicular, then F is not going through, so we say there's no flux. So flux is defined to be the integral of F dot ds, right? And so we not only need to know the value of ds, but also the direction. Fortunately, we can find out this ds as a vector just using that formula, Ru cross Rv, and that will give you naturally, the vector ds, the normal direction times the area. Oh, we need a du dv because it's also ds. So as before, we could have a very complicated Ru and Rv, but we are mostly interested only in three cases. One, the surface is z as a function of x and y. Then we have ds is just a negative dx, negative zy, and 1 dx dy. Alright? Oh, be careful about one thing. When you have an integration over a surface, then you have to say which is the positive direction of this ds, because you can say the surface has two faces, right? It could be this one or that one, right? Which one is n? Well, it's hard to say when you have just a surface like that, because either way would be okay. So we have to choose a direction, and that usually is possible. Say you have a sphere, then you can say the outward is your direction, right? Or you can choose inward, but by default we choose outward. Or a cylinder, then you can choose the outward as your positive direction. Because if you choose ds to be the opposite direction, then the integral would be the opposite of that, right? So we have to choose one of them. But choosing one of them is not always possible, and there is something called a Mobius band, Mobius strip. You can check online. This is an example of something called a non-orientable surface, which means you cannot consistently choose a positive direction. If you move along this band, you will see first you choose this to be n, then somehow you move along surface, and in the end you will get n in the opposite direction. So we won't consider that, okay? For us, that's something we don't consider. We will only consider surface that is orientable. Orientable surface only. And by default, we will choose n to be the outward. Let's say away from some kind of center. And if it's a surface like that, then we choose to be upward. Say z equals a function of x and y. then you can choose this way or that way, right? We choose the upper one. And how do you say it in vector form? We choose this to be positive. So the z component is positive, means it's upward. All right, so if your surface happen to be, you have to choose n to be the negative one, then you will change everything to be negative. So this is Vx, Vy, and negative 1. Okay, so if your surface, the direction you choose for this surface is downward, then you change to that. Okay, we will come to that at some point. Okay, but by default, we will just choose this. Okay. All right, this means upward. Our second case, circle, or let's say cylindrical. Let's say it's part of cylinder. Okay, so it's like that. And then you have this outward, right? So this ds, if you remember, we said it's a r sine, no sine, r d theta dz times n, and this n is just horizontal vector. So n is just a cosine theta, sine theta, 0, right? So when you integrate that, you can just change to f dot cosine theta, sine theta, 0, then r d theta dz. Right? And if you have a sphere, then out would be, n would be, let's say it's r divided by the capital R, the radius, right? Which means x, y, z over the radius. Then our ds is just this n, then it's r squared sine phi d phi d theta. Okay, so that's your inner product part. That's the surface element. Okay. Alright, so actually we only need to worry about these three cases. Okay. X, Y, it's here. This one. Oh, I didn't write on the integral for this one, so let me write on here. So if you want to integrate, then you just write on f dot this thing here, negative fx, zx, negative zy, and 1, and then dx dy. Alright, and for a cylindrical face, you write on this, but for spherical face, you write on that. Alright, so let's see example one by one. The first one is a sphere, part of a sphere. So let's integrate over just upper hemisphere, and so this is S, this is F, and then let's see what is F. F is X, Y, 2Z. You do it, and this ds is choose to be outward. Okay. And since this is a sphere, or let's say, what is a sphere? The sphere is x squared plus y squared plus z squared equals, let's say, 4 again. And so what is the upper means? Upper means is positive. Alright, so the radius is 2. So let's write out the integral. So you have x, y, 2z dot, remember, and x, y, z over r, and r equals 2. And remember, this x, y, z, they are not independent because they must be on a sphere. So it must satisfy this condition. Then what is this ds? It's just r squared, which is 4 sine phi times d phi d theta. And the range for theta is 0 to pi, and for phi it's 0 to pi over 2. Alright, so let's see what we get. 0 to 2 pi, 0 to pi over 2. Okay, let's do the dot product. X squared plus y squared plus 2z squared over 2 and times 4 and sine phi d phi d theta. Alright, and you can cancel the 2. You get 2, 0 to pi, 0 to pi over 2. Okay, what is this? You have x squared, y squared, z squared, which is just 4, right? But you have an extra z squared. How do you do that? Z squared equals r times cosine phi squared, right? Then you times sine phi d phi. Okay, that's pretty good. Oh, this is d phi. Then you can see this theta can be done it by itself. So just 2 pi. And for the phi, we can 4 plus 4 cosine phi squared, and then you can combine them. Right? Okay, that's pretty good. Then look at factor of 4, so you have 16 pi. Then the integral will give you, now you have 1. Okay, let me just get rid of the negative sign, put it in front. Then you have a cosine phi plus cosine phi over cube over 3. Right, like that. And then if you plug in half pi, you get 0. Plug in 0, you get 1 plus 1/3, but it's negative cancelled, so you get 4/3, and that's 64 over 3 times pi. Alright, that's your result for the flux integral. Okay. Second one, it's a closed surface. Closed surface means it's a boundary of a 3D region, and this time the 3D region is bounded by 2 surfaces. And it's this one and this one. Bounded. Okay, so let's plot it. This is y. Y equals x squared plus z squared, so it's a paraboloid, but in the y direction. This is z, this is x, right? So, and this is y equals 1, so it's the 3D region here, right? So let's see, what is the surface of this guy? It has 2 parts. It has this S1 and this part, S2. And by default, we choose the outward direction to be positive. So just as I show here, this is an S2 as a vector. I mean ds2, or ds2. This is n, and this is also n, right? So let's find out the integral over this surface of 0 y negative z times ds. So it has 2 parts, so let's do it in 2 ways. I mean, do 2 steps. This is and you don't have that anymore. You have S1 ds and S2. Okay, what is ds for s1? S1 is this n is just a j, right? It's in the y direction. So the first one is pretty simple. 0, y, negative z, dot 0, 1, 0. And what is ds? Okay, let me call this I1, and this I2. So let's do it step by step. I1, and then you have what is ds? Okay, I'm talking about this circle here, right? This circle. What is a circle? This circle is x squared plus y squared equals, sorry, z squared. Z squared equals 1. Okay, it's not in x and y, it's in x and z, but it's just a change of a variable, right? It's not y, it's z. But we can use the same idea. You know, you can use polar coordinate for that, but now polar is in the x and z, not in x and y. So you can, or you can just write down dA here, right? Because it's a, it's a planar thing. So that's what you have, and then this is just x squared plus z squared greater than or equal to 1, right? So what is that? If you take the dot product, it's y, just give you y, right? And what is y? Y equals 1. Oh, that's just area. Oh, then you can, skip the integral, write on this directly. This is a circle, right? So it's just pi. R squared equals pi. So done, right? Okay, let's work on the second part. Second part is not so simple because it's a paraboloid, and a paraboloid is neither a sphere or a cylinder, so we have to use y as a function of x and z. So we need to write down 0 y negative z dot. Well, what do we do here? Now we use dx and dz, right? And it's, if you project onto xz plane, you get the same circle. But what is this vector? Remember when we said z as a function of xy, we will get this vector. Negative zx, negative zy, and 1. Right? Now we have z as a function of x, y as a function of x and z. So you will have y as a special one, and then you have negative yx and a negative yz, right? But is this the one we like? This is positive. It means it's in the positive y direction, right? But we happen to have in the negative y direction because that is outward for us. So for our case, we should have a negative sign in the front. Okay, so you will have yx negative 1 and then yz. And what is y? Y equals x squared plus z squared. So we're plugging that into this term. Alright, and be careful, I'm going to calculate here. So I2 equals the integral, the dot product will give you negative y minus z times yz. And what is yz? Yz equals 2z. Right, take a derivative. So times 2z. And then dx dz. Okay. And how do we do that? We have x and z, but we don't have y. Okay, what is y? Y is x squared plus z squared. So this is negative x squared minus z squared, and another minus 2z squared and minus 3z squared. Right, that's what you have. That's a lot of negative sign. Then you have negative dx dz. Okay, over that circle. Disk. Oh, this is z. So since it's a circle, let's switch to the polar coordinate. But remember, now polar means in xz, not xy. So we have r d theta, and then polar negative sign. Then x squared plus 3z squared, and x squared plus z squared equals 1. So, oops, it's not a 1. Sorry. X squared plus z squared equals r squared. And then you have 2 times z squared, and z, well, if you do it this way, then z equals r times sine theta squared, like that. Alright, then you have r is from 0 to 1, and theta is from 0 to 2 pi. Alright, so that's your integral. And then you have 0 to 2 pi, and the inside you have, you can factor out all of the r stuff. You have r square. Alright, then you have 1 plus 2 cosine, sine 2 sine theta square. Is that correct? Yeah, I think so. Then r have another one, so r cubed dr. Right, so you can do separately for r and theta. So for r, you have just r to the 4th over 4, 0 to 1. And for theta, you have theta plus, and this one will becomes, 1/2, 1 minus cosine 2 theta. So cancel the 2. So you have theta. Wait. So actually have the 1 plus 1, so it's 2. Then you have 2 minus sine 2 theta over 2. And plug in 0 to pi. And once again, this is gone. So this is 1/4 times 4 pi. So the answer is just pi. Oh, that's a long way. Alright, is that done? Almost. We have to add this to that. Oh, they're both pi. So it's 2 pi. So the total integral is just 2 pi. Okay. Alright, let's see if this makes sense. It's always good to check. Let's see. Y is positive. So the vector field is like this way. And z is could be positive, negative, so it doesn't matter actually. Yeah, well, let's see. Y is positive here, so this integral should be positive, right? Because on this surface, y is positive. And here, negative z means if z is positive, it's going down. Oh, so it's inward. And y is this way. Is this correct? Oh, I missed that negative sign, right? See here? There's negative sign. I missed that. So it's negative sign. So the total integral is 0. Yeah, that makes more sense. Well, yeah, I will tell you why it makes more sense later. Okay, because we have something called a divergence theorem that tells us this integral should be 0. Okay. That's why we like this closed surface, because we can predict what it is. Okay, so the answer is 0. And be careful, I missed the negative sign there. All right, let's see one more example. The third example is the same curve, same surface we did last time. It's that cylinder. And that's, remember, that's x squared plus y squared equals 1. And this is z equals 0. And this is z equals 1 plus x. So it has a top face, bottom face, S1, S2, S3. So this time we still have a closed interval, closed the surface. And let's find out the integration of let's see, y and x, and 1, and let's make it even, 0 dot ds. Well, let's do z ds. Okay, and I can already see it's not going to be 0. Okay, let's see what it is. So you have to do it in 3 steps, right? Because you have 3 surfaces. It's a long problem again. So you have to do S1, and S1 is pretty easy if you can see it, because what is ds? ds is, this is n, right? And n is 0, 0, -1 because it's pointing downward. So when you take the inner product, you get nothing but negative z. But what is z? Z equals 0. So this once again equals 0. Alright, lucky for us. So let's do S2. Y, x, z times, alright, what do we have this time? This time we will have z as a function of x and y. So this will be, and this time the n is upward. So we can write on negative zx, negative zy, and 1 dx dy. And that's over a circle. So this S2 means x squared plus y squared is less than or equal to 1. Alright, so let's take the inner product. And this z equals 1 plus x. So this means that equals negative 1, 0, and 1. So we would have negative y plus z and dx dy. And z equals 1 plus x. So that's what we have. Okay. And this is x squared plus y squared is less than or equal to 1. So once again, we will switch to the polar coordinates. It's negative r sine theta plus 1 plus r cosine theta, r dr d theta, r from 0 to 1, theta from 0 to 2 pi. Okay. And if you have some experience, you should realize that when you integrate this sine theta over this d theta, you'll get cosine theta, negative cosine theta, and plug in limits, it's gone. Cosine theta will give you sine theta, plug in limits, it's gone. Okay, so all we have is just 1 times that, which means the area, and the area of the circle is just pi, because the radius is 1. So we're done with the second part. Okay, the third one is the surface, cylindrical surface. And y, x, z dot, what is the cylindrical surface? Well, it's this way, right? N, and n equals cosine theta, sine theta 0, because this is a cylinder, right? So dot, actually because I equals 1, so cosine theta is nothing but x and y and 0. Okay, so that's your n. And then what's your ds? ds is r d theta dz. And once again, the limit is a bit complicated. Let's take the integral first. So you get y times x times y, so it's 2xy. Or you can just say 2 cosine theta sine theta. And I equals 1, so you have d theta dz. But theta is easy, or you have to switch their order. So if you remember, z is from 0 to 1 plus cosine theta. Right? You know, because z is from 0 to 1 plus x. And 1 plus x means 1 plus cosine theta. So that's your integral. Alright, we can say you have what do you have? So you have dz. So you plug in the limits. You have 2 cosine theta sine theta times 1 plus cosine theta d theta. Right. So this time we will combine sine with that, and once again I have this negative sign. I will try to remember it. 1 plus cosine theta d cosine theta. Okay. Well, what is that? That's a bit strange. So you have negative, you have 2 cosine theta square over 2 and plus 2 cosine square, so you have 2 times cosine theta cube over 3. And then whatever you have, it will be gone because, you know, it's periodic function, so that's 0. So the integral is 0. Does that make sense? Yeah, it makes sense. Because we integrate x, y, right? Over this region, and it's symmetric region. So yeah. So anyway, so what's the total? The total is 0, and what's the second one? Pi, and the third one is 0. So the total integral is pi. And is that correct? Let me think. So this integral is pi r squared. Yeah, actually it is correct. It's pi. Well, okay. Now I will tell you why. Okay, so that's it for this chapter. And you just do the homework. And actually we have covered everything that will be tested. So the next lecture will be about 6.8, which is optional. It's just for you for your knowledge. Okay, it won't be tested. Okay, so that's it for today. Bye.